So the next one I am picking to show you is an example of what happens when solution coefficient is the same. dy dx minus 3y plus 4e to the 3x equals 0. So this is another differential equation. It's not in the right form for us to use yet. This happens to be number 5. So what I'll do first is I'll get those two parts. So I'll get the associated homogeneous. So remember, the homogeneous part is when I remove the terms other than dy dx and number times y. So dy dx minus 3y equals 0, or I can rewrite that as dy dx equals 3y. And then I know that the solutions to that would be multiples of e to the 3x. So that my homogeneous solution that's going to be part of my answer is k e to the 3x, where k is a real number. Next, what I'm going to do, I'm going to rewrite the original equation in the right form. So I'm going to add, or I'm going to subtract that that 4e to the 3x term over. So I want to point something out here. Do you notice how, unlike the previous case, we have that the number 3 here on the right-hand side of the equation is the same thing that came out of the homogeneous solution. So you could say, well, why don't we take the same guess as always? So I'm going to take a guess, and I'm going to note that this is going to be the wrong guess. So the wrong guess would be to say that the solution to this equation would just be a multiple of e to the 3x. But here's the problem. Functions of the form number times e to the 3x are solutions to the equation when there's nothing but the dy dx and the 3y. So you'll see what I mean when we try to go through this. So let's say let's go ahead and try. So we would be saying that yp prime is 3, and therefore we're going to have yp prime plus or minus 3y would be, sorry, not 3, it would be 3a e to the 3x. So we're going to get 3a e to the 3x minus 3 times yp, a e to the 3x. So there's your yp here, whereas this whole thing here is yp prime. Well, it doesn't take very long to look at that and notice that here we got 0. You can't set 0 equal to negative 4 e to the 3x. The thing on the left-hand side is a constant function. The thing on the right-hand side is an exponential function. As functions, they can't be equal. And for that reason, it's going to be really important for us to adjust our guess. So we need to think of functions that might generate an e to the 3x term in them, but that wouldn't be the only thing in their derivative. And the moral of the story is, when your guess fails, multiply by x. Now, to show you why that might work, because I think sometimes this is intuitively hard to see, let's go ahead and solve this problem by after we do the guess, we'll solve it by integrating factors, and we'll see where that came from. Let's change our guess. No, bad guess. Let's change our guess. So we're going to, instead of trying to guess just a multiple of the e to the 3x, we're going to guess x times a multiple of the 3x. So we're going to guess a times x e to the 3x. Now, the thing that makes this attractive is if you look at what its derivative does, we're going to need the product rule. And therefore, we'll get a times e to the 3x plus ax times 3e to the 3x. And this is the major advantage, is that we'll be able to generate some multiples of this that aren't just a completely multiple, but scalar multiples of 3. And that's where the special comes in. So yp prime will be a e to the 3x plus 3a x e to the 3x. And yp prime minus 3yp will be that minus, we're taking 3 times our original yp, so 3a x e to the 3x. And then we want to set it equal to the right-hand side of our original equation. So going back and looking up at the original equation up here, there was a -4 in front of the e to the 3x. So let's combine like terms on the left just so it's a little cleaner and we can see what we have. You'll notice this was done on purpose, and that's what makes it so beautiful, that those terms with the x's in them, the multiples of x times the e to the 3x, they cancel. So what we're left with on the left is a e to the 3x, and we're setting that equal to -4 e to the 3x. And so we conclude that a must be -4. And therefore, our yp is -4x e to the 3x. And we get as a general solution, we're going to take that homogeneous part from here, and we'll add to it -4x e to the 3x. So to show that this is not just some sort of crazy guess that worked in this case, let me point out how this one would solve by an integrating factor so that maybe you'd be more convinced. So I'm going to shrink it a little down here so that we can solve the same problem with integrating factors without doing a lot of movement. So I have dy dx minus 3y equals -4 e to the 3x. My integrating factor would be e to the -3x. So I'm going to take e to the -3x and multiply it by the right-hand side. Set that equal to e to the -3x multiplied by the other side. Now what you'll notice is you can simplify the right, and it becomes just -4. So on the left we have e to the -3xy's derivative equals -4. And then what we want to do is integrate both sides. So on the left we get our integrating factor times y, and on the right we're going to get -4x plus c. And then when we divide both sides by c, or by integrating factor, we get -4x e to the 3x plus c e to the 3x. So you can see we do in fact get the same thing. And so that, my friends, is why this strategy always works. And if it turned out that your right-hand side was like x squared e to the 3x or something, you just always multiply by an extra power of x. And so those are two examples of how this might work. And I'll create a couple more video solutions later on.